So welcome. We are about to prove the fundamental theorem of arithmetic. We have laid the foundation, so now we can actually go ahead and prove the fundamental theorem. So how are we going to go about this? Well, the good news is we've already done part of the work. We have already established that every natural number greater than 1 is either prime or a product of primes. So all we have to show is the uniqueness side. And so that's what I have written here. All we have to show is that uniqueness holds. And we're going to go about this proof via induction. So specifically, for n greater than 1, we are going to let the statement S of n be the statement n has exactly one prime factorization up to order. So if we do this, the base case, n equals to 2, is automatic, since 2 is prime. So there's nothing to show here. So now, we're going to go by principle of strong induction. So now assume that the statement S of n, or I'm going to write S of k, is true for each k less than n. And so here we're using the principle of strong induction. Now, if n is prime, then we are done. So suppose n is composite. Now, we have already established that a composite number is a product of primes. So let's go ahead and say that n be P1 times P2 all the way to some p sub r, but also Q1, Q2 to some Q sub m, where each p sub I, q sub j is prime. Now I want to make a clear point here. It may seem that we are going about this via contradiction. We have two different prime factorizations of n, but actually we are not going by contradiction. We're saying that we're choosing two prime factorizations. Not necessarily that they're different, but what we are going to prove, and this is what makes this direct, is that they in fact are the same prime factorization. So what we are showing is if we have two prime factorizations for n, they really are the same factorization. And so what we are going to show is that r is equal to m, and after a relabeling of the indices, we can choose P1 to be Q1, P2 to be Q2, and then PR is equal to QR, since we're going to show that m is equal to r. So how does this go? Well, we are essentially at this point almost done. All we have to do is look over here. We see that P1 is a factor of the right-hand side, so P1 divides Q1, Q2 times all the way to Qn. Corollary 145, which is a corollary of Euclid's lemma, tells us that if a prime divides a product of natural numbers, a1 through ar, then the prime must divide one of those quantities. So, in other words, corollary 1.4.5 implies that P1 divides Q sub j for some j. But now, without loss of generality, we may assume that P1 divides Q1. Since Q1 is prime, we have that P1 must equal Q1. Because P1 divides Q1, Q1 is prime, so the only factors Q1 has is 1 and P1, but Q1 is greater than 1, so it must be P1. So now we have P1 is equal to Q1. Let's come back to our factorization over here, and now we're going to divide both sides by P1. So then n over P1 is equal to P2 all the way to PR, Q2 all the way to QM. So we have this here. But n over P1 is less than n. Since n over P1, we know that n was not prime, so this is greater than 1. But we also know that this is less than n. That was supposed to be a 1. Our induction hypothesis implies that R is equal to M because by our induction hypothesis, both prime factorizations over here are exactly the same. So we can only have R primes on both sides. So R is equal to M. And after relabeling, we have P2 equals Q2, Q3 equals P3 equals Q3 until we finally get to PR is equal to QR since R is equal to M, and that shows uniqueness. And so we are done since we have established that this is true, and now strong induction tells us that the statement is true for every n greater than 1, and that's it. Fundamental theorem has been shown. And so we have done it. But while the proof right now is it was not as bad as some of the ones we have done up to this point, and it really just boiled down to this corollary, it's important to keep in mind that we really have been climbing up a mountain. And this is a great picture that is in the book, following the proof of the fundamental theorem. So we started off talking about the well-ordering principle and the equivalence of the principle of mathematical induction, strong induction, and well-ordering in the very first lesson. The second lesson had us going into the division theorem and statements that we had covered in structures. So we went into the division theorem, we proved it then. Then our lesson after that established the Euclidean algorithm, Bézout's lemma, and Blankenship's method. And then following that, in the last lesson, we established Euclid's lemma. And so we have climbed this mountain, and along the way we solved different Diophantine equations. We established ways of finding the solution set to set the Diophantine equations. The fundamental property of primes in the book is what we are calling Euclid's lemma, so just a little pointer there. And now we have proven the fundamental theorem. Now, my one disagreement with this drawing is that it has Fermat's theorem as a mountain off in the distance. Fermat's theorem is more like the moon, and so we have to to get there, we will have to develop essentially NASA and all the rocket science to get us there. And so technically that's way off there. But that's the key thing, is that right now this mountain that we are discussing, with some exceptions being Bézout's lemma and some of the modern techniques, this is what was done in ancient Greece. This is work that Euclid wrote down. And so now we're going to move on in the next lesson into the more modern side. So the next lesson will have us review the beginnings of modular arithmetic, which you have seen in structures, but we're going to go ahead and use it to prove number theoretic results. And actually, modular arithmetic is a rather recent thing when compared to what we have done with work that dates over 2,000 years ago, over 2,000 years. So with modular arithmetic, it's actually due to Gauss in 1802. And so it's something that is just over 200 years old. And so that's what we're going to be doing in the next lesson. But for this lesson, we have proven the fundamental theorem. Now let's establish some consequences of the fundamental theorem. So before we get started, I want to go ahead and introduce some notation, which is similar to sigma. So notation. So if I write j equals 1 to n of a sub j, we know that this is the notation a1 plus a2 to an. And in structures, you have seen the notation, the product symbol, j equals 1, aj, and so now this here will be a1, a2, and then we multiply all these, and then we get a sub n. Alright, so one way of writing the fundamental theorem, so what the fundamental theorem tells us that if we have n, we can write it as a product of primes, p sub j equals 1, let's call this here r. But I'm going to make a bit of a note. When we were proving the result, we didn't really care about having repeats in the primes over here. But because we know that there's a unique prime factorization, we can go ahead and say that we can always write n as equal to a product from 1 to r, p sub j to the a sub j, where each p sub j is a distinct prime. So we have this here. And so now what we are going to show is this proposition that is using this notation. It's saying, here we have a number that is greater than 1. We have its prime factorization, which we're going to be writing in this way. And then a natural number d divides n if and only if d can be written as a product of primes where each of the exponents appearing are at most that exponent a sub j. So let's go ahead and show that. So let us go ahead and prove the proposition. So assume the forward direction, so specifically d divides n. By definition, there exists some m such that d times n, and this specifically is a natural number, so there exists some natural number m such that d times m is equal to n. By the fundamental theorem of arithmetic, we have that d is equal to some collection of primes, q1, q2, all the way to qr, and m is equal to v1, v2, all the way to, let's go ahead and call this v sub s. And so we have these two prime factorizations, but then, since then n, which by assumption is equal to j equals 1 to k, p sub j to the a sub j, is equal to q1, q2, qr times v1, v2, vs. And over here, I just realized I didn't mention this, the qj's and vi's are primes. We're not assuming necessarily that they're distinct, but that we know that we're assuming that they're primes by the fundamental theorem. And here's what we're going to do now. Because we have uniqueness, q1 is a factor of the left-hand side. So that means that q1 has to divide one of the factors appearing here, but if we write them all in terms of their primes, what we end up having, as we saw with the corollary when we were proving the fundamental theorem, is that q1 has to divide the product, but each of those are primes, and so the same argument we used over here to deduce that p1 was equal to q1 allows us to then deduce that q1, q2, qr, v1, v2, vs, all these primes have to be equal to at least one of these p sub j's. So, by applying corollary to Euclid's lemma repeatedly, we get that d is equal to a product from j equals 1 to k, p sub j to the v sub j, where 0 is less than or equal to v sub j. So remember, it could be the case that this v sub j is exactly 0, in which case we have v to the 0, which is going to be 1, p to the 0, which will be 1, and so that's perfectly fine. But there's only the k distinct primes appearing on the left-hand side. And so applying the corollary tells us that each of these q1 through qr has to be one of these p sub j's. And so we have this. And so now what we want to do is establish that each of the b sub j's has to be less than or equal to a sub j. Well, the way we go about that is by dividing. Because now, consider n over d, which by definition of how we constructed m, this is equal to m. But now, applying the exponent rules that we know tells us that this here is going to be pj to the a sub j minus b sub j. Since m is a natural number, we have that a sub j minus b sub j has to be at least 0. But that's what we wanted to show, because now we have 0 is less than or equal to b sub j by the construction above. But now we also have that this is less than or equal to a sub j by this inequality, which shows the forward direction. And so now all that's left to do is to show the converse, which is not so bad. So for the converse, let's go ahead and write d. And this is really the same, the argument for this one is embedded in what we just argued. So d goes from 1 to k, p sub j to the b sub j. And we know that 0 is less than or equal to b sub j, less than or equal to a sub j for each j. And now what we are going to do is consider the product over here with the a sub j's minus b sub j's. So specifically, we use the fact that since a sub j minus b sub j is at least 0, since we have this assumption here, the quantity m given by the product has to be a natural number. But then m times d is going to be equal to n. Since when we multiply these out, we're going to collect it like the exponent powers, the a sub j minus b sub j's, plus the p sub j, since we have distinct primes. And so the b sub j's and the negative b sub j on this one will cancel, and we're just going to be left with the product of p sub j to the a sub j, which is the definition of n. And so therefore, d divides n. And that concludes the proof, and we are done. So as a consequence, we actually can determine combinatorially how many factors a number have. So more specifically, let n be greater than 1, write it uniquely in terms of its unique prime factorization in this way, where each of the p sub j's is a distinct prime. Then the number of total positive factors of n is given by this formula. So why is this the case? So let's see. By the proposition, if d divides n, then d has the form j equals 1 to k, p sub j to the v sub j, where 0 is less than or equal to v sub j, which is less than or equal to a sub j for every single j here. And so we have this. So how many possibilities are there for each b sub j? So for each j, there are a sub j plus 1 possibilities for b sub j, because we're including 0. And so we have 1, 2, 3 all the way to a sub j, and 0, so we have a sub j plus 1 possibilities for b sub j, and so therefore there are exactly j equals 1 to k, and then we multiply the different possibilities for each exponent that we have for the v sub j's, so that's a sub j plus 1, and so now that concludes the proof, and we have a formula now for deducing the number of positive factors of any given number. And if we look at the next example, we can look at the number 126,000, and we write its prime factorization. It's 2 to the 4 times 3 squared times 5 cubed times 7. And so now we have that it's not the primes themselves that matter, but the exponents. So we have 4, so 4 plus 1, 2, 2 plus 1, 3, 3 plus 1, 7 to the 1, so 1 plus 1. So there's 120 distinct positive factors for 126,000. So next, let's go ahead and define what it means to be a least common multiple. So in the case, we have already defined the greatest common divisor. Now, the least common multiple of a and b is the smallest integer m for which a divides m and b divides m. So we can express it just as with GCD symbolically by saying m is equal to the LCM of b. And then when we look at the least common multiple of 3 and 5, well, 3 and 5 are relatively prime, so we multiply them, we get 15. In the case of 12 and 10, 12 and 10 are not relatively prime. And so in that case, we have that we can't just multiply them, the two, and get 120, because that would be too much. But 60 is in fact the least common multiple of the two of them. And so here we have 12 divides 60, and 10 divides 60. And so this is the smallest integer. And so had we multiplied them, we would have gotten 120. And yes, 12 and 10 divide 120, but we want the smallest. So next we're going to go ahead and prove the following proposition about natural numbers m and n. And here m is given by this prime factorization, and n is given by this prime factorization. An important note is that in this situation we are assuming that a sub j and the b sub j's, we're allowing them to be at least 0. Because in the way that it's being written, we need to be a bit careful because, for example, what if 2 divides m, but 2 does not divide n? The way that we were writing this factorization before, 2 wouldn't appear as a p sub j. And in this case, we want 2 to appear for both of these, just that if 2 doesn't divide n, then we would have 2 to the 0 appearing as the b sub j. And so just want to make that point for this statement. So next, okay, so let's go ahead. What we want to prove is that the GCD of m and n, we can actually write what the prime factorization is based on the factorization of m and n. So specifically, it's going to be the p sub j's to the minimum of the exponents of aj and bj, whereas for the least common multiple, it will be the maximum of the aj and bj. I will show the GCD case and mention that for homework, exercise 20 of 6.2 will have you prove the statement about the least common multiple. So for the proof, so let's go ahead and let D equal the GCD of m and n. Then D divides m by definition, and D divides n. By the previous proposition, so this is specifically the proposition that we just did in terms of proposition 6.2.1. So we have shown that if we have a factor of some number, we know exactly that the exponent has to be at most that exponent. So applying that, we have that D is equal to the product from j equals 1 to k, p sub j to the c sub j, where c sub j is less than or equal to a sub j, and c sub j is less than or equal to b sub j. But this condition tells us that it can be at most a sub j and b sub j, and so specifically we have that c sub j can be at most the minimum of a sub j comma b sub j. And so that's what we have from these two inequalities. And so now we want to show that equality does actually happen. So suppose for a contradiction, actually we don't need contradiction here. Now, applying the proposition again, shows that the product from j equals 1 to k of the p sub j's to the minimum of aj comma b sub j is divides. So now we get to prove this very nice proposition, which tells us that if m and n are natural numbers, the product of the GCDs of m and n and the least common multiple is exactly m times n. So let's see this. So the proof is quite nice. So if we use a notation, so I'm just going to sketch over here the proof. I'm going to use a notation here. So we see that this is j equals 1 to k, p sub j to the a sub j plus b sub j. Whereas if we do the GCD, that should be a multiplication symbol. We have that this here is the minimum of aj comma bj plus the maximum of aj comma bj. And so we have this here. And so what we want to establish is that this here is the same as aj plus bj. If we show that, we are done. So let's investigate. Plus max of aj. Oops, that should be a comma. Now, we're going to break this up into two cases. If aj is less than or equal to bj, and if aj is greater than or equal to bj. We do have a bit of overlap, but let's go ahead and just do away the overlap there. Let's just do it this way. Alright, if aj is less than or equal to vj, then the minimum of the two is going to be a sub j. But then the maximum is going to be b sub j. And so we have that. If aj is greater than b sub j, the minimum will be b sub j. And the maximum is going to be a sub j. So this is equal to aj plus bj. And we are done, because that's exactly what we want to show. We now have that the exponents match up. And so that's another nice application of the fundamental theorem. And so we have this proof. And as a consequence, we get that if m and n are relatively prime, then the least common multiple is going to be m times n. And so now this follows automatically, because if they are relatively prime, then the GCD will equal 1. And so then the least common multiple of m and n must be m times n, which is what we saw if we take 3 and 5. Their least common multiple is 15. We just multiply them with each other. And so now we have this as another consequence of the fundamental theorem. So now we're going to move on and prove, actually generalize a statement that is covered in structure, specifically the square root of 2 is irrational. We're going to go one step further and prove that the square root of n is irrational whenever n is square free. And so specifically we want to make sure that if n is not a perfect square, then it will be always an irrational number. So how do we go about this? So we're going to first prove a lemma. If R and S are natural numbers, such that if s squared divides r squared, then s divides r. But we're going to prove this via the fundamental theorem. But in structures, this is proven using going via the contrapositive. So how do we go about this? Well, we have, so for the proof, let's go ahead and let S and R have the following prime factorization. So make sure you write R first. A sub j, and S is also equal to j equals 1 to k, b sub j to the v sub j, where each b sub j is a distinct prime. And because we're choosing the same prime factors to appear in both R and S, we also require that the exponents are less, that 0 is less than or equal to aj and bj. So we're allowing for the exponents to be non-negative. They could be 0. So we have these prime factorizations from the fundamental theorem. So next, let's go ahead and consider r squared. So then r squared, and actually let's use also s squared, are of the following form. Pj twice a sub j and s squared, j equals 1 to k, p sub j twice b sub j. So this is just applying the squares to both sides. We're squaring the product. These are distinct primes, and it'll be p to the aj, p sub j to the aj, quantity squared. So exponent rules, we have 2 times aj in the exponents for each. So we have this. Now we use the proposition. By the proposition 1.5.2, we have that 0 is less than or equal to twice b sub j, which is less than or equal to twice a sub j, since s squared divides r squared. So here we use the proposition. We have s squared divides r squared, so that gives us this inequality. But this inequality then tells us that b sub j is at most a sub j. So we have this inequality now as a consequence of that. But the proposition is an if and only if. So applying the proposition once more, implies that S divides R, which is what we wanted to show, and so now we are done. And so that's the beautiful part about this if and only if condition. We first use it in the sense that S squared divides R squared, we get this inequality, and that inequality allows us to reduce it down to this inequality here, but then we can reapply it in the reverse direction to get that S divides R. And so that's a nice application of the proposition here and the fundamental theorem to prove this in a new way than was done in structures. And so now we can get to the following statement. If n is a natural number that is not a perfect square, then the square root of n is an irrational number. So let's go ahead and prove this. We're going to go by contradiction. Suppose square root of n is a rational number. Also, an observation before we continue. N is not a perfect square. Implies that square root of n is not an integer. So I just want to make, this is something we're going to be coming back to in a moment. If n was a perfect square, it must be an integer, and in this case, we are assuming that it's not a perfect square. So we know that for a fact the square root of n is not an integer. So let's now suppose that it is a rational number. So then there exists a and b in Z with the GCD of a and b being 1 such that the square root of n is equal to a over b. Squaring both sides. Gives n is equal to a squared over b squared, which then gives b squared n equals a squared by multiplying b squared on both sides. But then b squared is a factor of a squared, so b squared divides a squared. So we have this. Now lemma 1.5.7 comes to the rescue and tells us that if b squared divides a squared, then b divides a. And now we have to take a step back. If b divides a, and the GCD of a and b is 1, that means that a and b are relatively prime, then the only way that b could divide a is if b is equal to plus or minus 1. And so we have b is equal to plus or minus 1, and thus a over b is equal to plus or minus a. But a over b is the square root of n. So now this is an integer, which is contradicting our assumption that n is not a perfect square, and that's our desired contradiction. QED, this completes the proof, and now we have shown that the square root of n is always irrational whenever n is not a perfect square. And so that completes it for the fundamental theorem. And so we are done with at least the aspects of number theory in this course that pertain to what the ancient Greeks did. And in the next lesson, we're going to transition over to the language of modular arithmetic and start to develop it. And so that's going to be something we're going to be devoting the next several lessons. And then after we have developed the language, we're going to start proving results that actually date back to Fermat himself and statements that he claimed to have proven but did not. And we will see how the language of modular arithmetic makes their proofs so much simpler. And so we're going to get a lot of practice in using modular arithmetic to deduce number theoretic statements in the coming lessons.